it only transduces self-generated sounds. So if you look at the things like on the left for earbuds and phones and other devices like that, glasses, the idea is it picks up only me talking. It doesn't pick up anything that's airborne.
Hey everybody, Dave Lindberg with a new episode THD Podcast. Thanks for checking us out. Thanks for subscribing. We see that our views are increasing lately, so I don't know what's going on, but thanks for that. Please like, subscribe, share, all that good stuff. Today we have a company, I thought they were out of Irvine, but maybe they've moved. But anyways, it's Syntiant, and they've made some pretty big moves recently, especially related to audio in the acquisition of Knowles MEMS microphone business. So we're going to find out what's going on there. We've got the CTO, Steph Bailey, joining us. But without delay, let's give a shout out to our sponsor, the ALTI Association. Please check out Barry Vogel's organization. Great networking for audio components and industry manufacturers, all the like. And without forgetting the AudioXpress, we always like to give them a shout out. They're a great aid in finding about what's going on in the audio industry on all levels from product to component. So we encourage people to subscribe to that publication. So let's say hello. We got Simon. Good morning, Sendai.
Morning.
Hey, and Steph Bailey joining us from the Vegas Strip, it seems.
Hey, David, Simon. Yeah, we are still based in Irvine. That is true. But my background is a little noisy, so I love the Strip. Here we are. Welcome to the Strip.
All right. So yeah, this is pretty big news. I don't know, it was about a year ago it started, but it's closed now, and Syntiant now owns the former Knowles MEMS business. So there's some pretty big synergies between edge processing and sensors on the edge as well. So maybe we can get into something and explain to people what's going on here.
Okay, great. Thank you. Yeah. So Syntiant was founded in 2017, and our focus at that time, what we felt was that there was an opportunity, an unserved opportunity where we had capability to provide a deep learning driven interface platform. Okay, which this has come to mean, AI, edge AI. It's kind of a shorthand for this. We'll talk a little bit more about what it means, and then we pieces go together, as you said. So basically, we started in 2017. We did an acquisition in 2022, and then we did this sensor acquisition, MEMS microphones, towards the end of last year.
Okay.
So let's talk about what when we say interface, what do we mean? And so definitely the discourse I can feel since we started. It's kind of coming towards us, I would say. Like I've seen Qualcomm speaking in these terms and some much bigger people that previously were just talking about edge compute and workloads and things like that. So our view basically is that, the interface is where the real world meets the digital world, right? Okay, so the digital world basically has two parts. It has applications that are typically run on servers, although in some cases they might be deployed down. Doesn't mean cloud. Some cases, like my laptop, is kind of functioning as a server if it's running application code self-contained. But generally speaking, that's the way we think of it. And the most valuable apps, a lot of them definitely do deploy on servers scaled out. Then how do we get to and from it? That's all these devices. So cameras, compute clients, mobile devices, earbuds, glasses, televisions, the works. Okay, and so the devices fundamentally exist. Their indelible responsibility is to connect the physical world to the digital world. In this case, people. They're definitely one of the most critical and valuable pieces of the physical world. But it can be other things too, right, that are not necessarily just people. Mm-hmm. So this is kind of how we view the lay of the land. So then let's go look at what's in an interface. Okay.
But
so what does this mean?
Just quickly, Steph, by other things,
yes.
in terms of sensor world, we're talking that could be weather, that could be animals, that could be noise detection. It could be all kinds of things that you're using sensors for, and then interfacing
chemical
that to
experiments. And yes, right. Exactly. That's right. Pretty much. So there's phenomena, that stuff that happens in the real world. And then a sensor's responsibility is to convert a phenomenon to a signal. So if it's air pressure, as a microphone does, then it generates a digital or analog, but we're focusing on digital in this particular presentation. We have both, a signal. And then, so that could be, in the case of an image, photons, light waves, and a pixel array, and then out comes a digital representation of the picture. So that's what the sensor does. Okay. And then the next thing that happens on our way up to generate a complete interface is we then want to run some programs that turn the signal into an input for an application. Okay. And so an example here of a super simple case that, Syntiant has pretty good experience with is to listen to a sound signal and report an input that's, I heard a window break. Okay. And distinguish from, I heard, a wine glass break, or I heard somebody bash a plate, or all that sort of stuff. So the program runs on a processor. And so basically the sensor, processor, program are the key elements, and then the input is what goes to the application. On the output side, rather than a sensor, it would be an actuator. So something like a driver or a speaker or something like that, but basically the same flow. Okay, so this is essentially what interfaces are built on. And so how we see the world of devices, terminals, interfaces to date is, the keyboard came along in a widespread way, and that was something like MS-DOS, and we were shipping 150 million units a year. Okay, so then next came the mouse, which supported the GUI, and that became easier, more engaging, more pleasant, more useful, and 3 times as many computers with GUI, Windows, and Mac were shipped. Okay, and then next came touchscreen devices, which basically combined the keyboard and the mouse and the GUI. And more useful, easier to use, et cetera. Okay, so, and again, boom, another 3x in terms of the deployment of devices based on the value that we see in it. Okay, right. So all 3 of those interface generations use only conventional processing. Okay, so what that means is that the world, us, we have to understand the interface. Okay, so basically, like, we learn how to type. We learn how to mouse and drag stuff around and stuff like that. So the next step, basically, what's brought by, revolutions in deep learning, revolutions in, big data collection and training mechanics and all those kinds of things, is to build interfaces powered with deep learning rather than conventional processing. Okay. And what deep learning brings is the ability for the interface to understand the world rather than the other way around. And so that gives you a more natural interface, which I think it's pretty clear will lead to, a larger explosion of digital physical interface devices as they're easier to use, more intimate, et cetera. Okay. And some examples of the types of things that are interface and that can be powered by deep learning. Conversational speech is an example that we have today. So we had quite a few generations of speech understanding systems today. The large language models that basically learn how to talk by ingesting, enormous amounts of linguistic content are the best we have. Vision, also deep learning driven, originally conventional processing, but essentially what happens is for inputs that are either large or noisy, deep learning is a better programming mousetrap. So vision, very quickly, as soon as deep learning was applied, the conventional techniques were pretty much left in the dust. Sound, it took a little longer. Other signals like vibration and so forth, starting to happen now too. So those are more noisy than large. So basically, this is generally what we felt was going to happen, and over the 8 years, it is happening. So good for us, fully for us. Okay, so in terms of what we offer, our vision when we started out was to again offer a complete platform for this deep learning driven interface. And just for clarity purposes, I think the key thing to understand here is that interface on its own, it doesn't do anything, right? There has to be an application. And then what you provide as a technology provider is building blocks. Okay, so even though you can see complete end-to-end type behaviors, that's not customers then have to put all that together to build their products. Okay, so we focused on a chip product that was going to run on very low power battery powered devices. Okay,
Mm-hmm.
our belief also is that the ideal terminal devices are all wireless, which means wireless communications and batteries. Okay, that's every one of these devices, if it could, would do that. Doesn't mean all of them will. But this was an area where there was no existing technology. The deep learning processors are things like NVIDIA chips and cell phone chips and laptop chips and stuff like that. So we focus on stuff that is can run long time running real deep learning workloads. Okay, so that's a Syntiant NDP chips. We have over 75 million of those shipped. Customers pick them because they have an energy constraint, or they have a size constraint, or possibly they have an economic constraint. So like if you had no economic constraint, you just use NVIDIA, right? It runs everything, it's great. But it drags an expensive chip, a bunch of DRAM, a whole lot of RBOM and power converters and so forth. So our goal is to plug these things into very small systems. We also sell turnkey deep learning models. Okay, so we started out focusing on sound-related stuff and acquisition, added a vision capability. We have over 50 million of our models out there in the world, and products you would cut open. Half of those roughly are on our chips, and half of them are on other chips. And then the final piece of it from that completed interface is the sensors. So we acquired that at the end of the year, over 20 billion. We actually invented the silicon MEMS microphone in 2004. You see how like royalty, you can buy your way into history. But yeah, so we're a world leading provider, $1.5 billion or more mics. We'll talk a little bit about some of the sensor technology going ahead. Okay. In terms of applications for AI specifically, I mean, basically on the microphone side, pretty much everybody is a current or was or will be a customer of our microphones. So not all of those are powered by deep learning. If we look into the types of stuff that we're powering with deep learning, with Syntiant technology, well, pretty limitless application space. So limitless is hard to capture all at once. So there's certain areas that are progressing, and then others will catch up. When we first started, we had focused on voice assistants, okay, basically for things like earbuds and remote controls. Mm-hmm. And what we discovered was the actual assistants behind the system were not that pleasant, were not that good, and the users, didn't enjoy working with them. So while we were able to provide the technology to make these lightweight battery-powered devices connect to voice assistants, in many cases, the users just didn't like it. With the improvements through large language models, they're getting a lot better and easier to work with and more pleasant. And, we are also focusing some of our model activity there too. So just go through a couple of the greatest hits, all the way down to hearing aids. So medical prescribed hearing aids, which have a really tight power and size constraint, to things like appliances where there's no size constraint, there's no power constraint, there is an economic constraint. And then one of the key requirements for a deep learning processor is it runs all the models. NVIDIA does on the server side. And so the critical evaluation, as we've had 3 generations of our technology out there, is can I run this model? Can I run that model? Can I run them all together? All those types of things are places where we kind of led. And then a lot of stuff in between. We'll look at an automotive example is fully worked at the end. Mm-hmm. Okay, so in terms of like what's next on our model side, so a lot of these model types, they're fairly well understood. What Syntiant brings to the picture there is models that run on very light hardware. Okay, so there's open source models, but they're big and they consume a lot of resources, which means you need a big and or expensive processor to make them run at whatever rates are required for the problem. So we make them so they're, embeddable and economical, like a, cheap security camera or a, $20, glass break sensor, things like that. So we're taking the same viewpoint so transformer models are basically, a revolution in the ability for the models to generalize on large data sets. Okay, so that's really what's happened is sure, you could build an architecture to try and train a convolutional or recurrent model with the internet. It wouldn't it wouldn't make heads nor tails of it. So the attention layers are what really broke everything open. And we're taking those same structures down into embeddable devices. So for example, we have a small language model product, which basically gives you a nice, pleasant, easy, high performance, single turn conversational bot, if you will. So large language models, you can talk endlessly to them and go off in any direction. And that's both their strength and their curse. It's hard. They lose their way pretty easily. But if you take something and specialize it down to, say, a video conferencing bar that you want to control with a speech interface, because it doesn't have a tactile interface, or it has a remote control at most, but no display, just tell it what to do. So either it's so simple it just does it itself, which they aren't, or ideally speech is the thing. Okay. And so we are able to take it. So you could say, turn on person tiling, turn on auto framing, turn on off framing, there's many different things we can do there. And so these models are small and run on the kind of cheaper processors that are in those devices. Okay. And then on the vision transformer side, also pretty magical stuff. You can basically, these models, you can provide a linguistic input, like tell me, find me the person in the red hat, and it will look at a picture and it will say, here's the person in the red hat. Or you can even drop in a picture and say, find this person. So it's multimodal. And again, those models exist at humongous scale in application services, but scaling it down to make it something that can be operable locally to build the interface of the device is where we focus. Okay, so
you've kind of got.
Sorry, go ahead.
Yeah, no, it's seeming like I'm just kind of thinking of like the low IQ application of listening versus the high IQ. So enabling that scale in application, like you mentioned, hearing aids versus refrigerators, and the amount of like just threading the needle. But it seems like you're creating a base level that could service a lot of endpoints.
Yes, that is exactly right. And again, I think it's just to uplift the interface from tactile visual, right? Visual is expensive in the sense that you need a screen and you need a bunch of things to drive, language on that screen to us, which is great for devices that carry it, right? And magical for creating stuff. But just interfacing with devices, it's expensive, it's cumbersome, it's so much drag, and speech is just more pleasant. And then similarly, like the vision transformer is really an up-leveling of the security camera capabilities we provide today. So today, one of the challenges with security cameras, this is a bit of mousetrap, is, okay, I detect a person. Okay, that's a base feature essentially upon which you build something bigger. The person, may move, they may cross cameras, or you don't reliably 100% detect every person every single time you look at them every time. Part of the way you detect them is you see them a few times. If we see them 7 out of 9, maybe there's a tree blowing in the background, or all sorts of different things, you basically filter over that. Okay, but then, so it's difficult to say then, did I lose that person across cameras or just because they walked in front of something or whatever? And so the visual transformer, because it looks at every single thing and it creates an embedding, and you say, find me this embedding, it's kind of like a person in that way. It's like you're locked on, right? Anytime you see it, you know that's it. And that, again, is a base capability that's a better mousetrap than where you start with the previous models. So it's really just building these interface building blocks to build applications so that the application developers don't have to wrestle with all of it soup to nuts. You start with sensory understanding capability. I hear a sound and it is an X, Y, Z, P, and Q, or I stream the sound, I get linguistic output, stream of linguistic output, I get speech output, all those kinds of things. Yes, that is right. Okay, so that's models. Okay, so thing one that we sell, models. Okay, and this is the sort of where we're working at the cutting edge. We have a whole package of other models we'll talk about a little bit in our final example. Sensors, two things basically to talk about. One, a couple of big buildings that pump out all these microphones. So that's certainly a step up in scale for Syntiant. It's been publicly stated that our objective is to go public in 2027, which based on our revenue and other intrinsics of the business is not ridiculous. We all say we're going public, but we have the scale. So we just working to get it together. Okay, so we're the only vendor today that's got end-to-end design and manufacturing. We have a fully outside of China flow, and we have a China local flow, Suzhou and Penang. Right. So basically, we have supply flexibility. For people who want, if you want to touch China or not. Okay, right, and then all of the manufacturing, quality support globally. All that comes with being a leader in the MEMS sensor, MEMS microphone business. Mm-hmm. Okay, so let's talk about our newest. So I talked about our newest models. Let's talk about our newest sensor. So microphones, great, very successful. One of the handful of sensors that have crossed the scale hump from tens of millions. I mean, basically, there's a couple of sensor types that have shipped into consumer volumes, IMUs and microphones being the two most prominent in that class, and then most other sensor types.
What does IMU stand for again?
Sorry, inertial motion unit. Okay, right. So it's
almost like a new word for gyro. Is that a fair way to?
Well, it actually does. So it does linear and rotational acceleration. So the rotational part is gyro, and the linear is linear, is an accelerometer. So accelerometer and gyro, and in some cases magnetic, some form of multi-axis magnetometer. Okay. Yeah. So if you look inside of every cell phone has one. Most earbuds have at least the 6-axis, which means no magnet gives you an exact orientation. The rest of it is relative. But there's gazillions of those shipped. So the microphones and the IMUs are kind of the granddaddies of scale today. Okay. And there's a big step to get over to scale into the billion plus units a year compared to the tens of millions of units a year. That's what I've come to learn in my 6 months as a microphone man. Okay. So one of the things then we did was basically look for instead of an airborne pickup, that's a microphone, a structure-borne pickup. Okay, and so the accelerometer is a structure-borne pickup, effectively, right? You move it this way, it reads something. You move it that way, it reads something else. But in many cases, there are structure-borne motions that really are best understood as sound. Okay, and again, understanding comes back to like a neural model, looking at a signal and generating an input to an application. Okay, so what we built here is a device that has characteristics very much like a microphone. Okay, it's called the V2S, or vibration to sound sensor product, and so it has the same wide bandwidth of a microphone. So if you slap it onto a metal material or something like that, and you're seeing, 10 kilohertz or something like that, it's capable of picking that up and faithfully reproducing that. Okay, so has a wide bandwidth, plugs into the system just like a microphone. So on a PDM, microphone digital interface, you can connect a V2S and a microphone on the same interface. So plug it in wherever you want. And one of the key things is it has environmental protection that is not doesn't come with an airborne microphone. You can environmentally protect airborne microphones, as you know. You of all people have quite a bit of expertise in this, but it's costly and expensive. So so the two key things it does basically is give you this microphonic type capability with protection, with economical protection. The other is it only transduces self-generated sounds. So if you look at the things like on the left for earbuds and phones and other devices like that, glasses, the idea is it picks up only me talking. It doesn't pick up anything that's airborne. Okay, so that is part of a solution that can generate really, really clear uplink for voice communications. Okay, so and that's one beneficial use of it. In terms of the industrial side of it, for example, if you want to only monitor the noises of your own machine, let's say you're in noisy factory. Okay. And so
Yeah.
just noise everywhere. Okay. So you use a structure borne sound pickup, and you're only picking up from your machine. So you're not being deceived by airborne sound from other machines or cross correlations or any of those kinds of things. So basically self-generated sound only. Okay. That also, we look at that for things like if you want to have a voice interface on a robot vacuum cleaner, right? You want to pick up the self noise and remove it so that lo and behold, you can talk to your vacuum cleaner, while it's driving around. So, and then on the protection side, automobiles are actually a good place for this. So they're subject to very, very, very harsh environment. And so our demonstrations we give at our shows today basically are something like you take a V2S and you put it on pretty much any service. It can even be like a watch. Okay. And it picks up sound, and it's pretty high quality with a little bit of tweaking. It sounds fairly realistic. It's not as good as airborne, of course. But once you add deep learning processing to that, then it can become pretty amazing.
And are there data sheets available for this? Because I can imagine if you did like a mux of an airborne plus this sensor, for wind noise elimination, there could be a lot of people hungry for this kind of solution.
Yes, absolutely. Yes, there are data sheets for all of our sensor products. Data sheets are freely available. For our processor products, it's the usual chip company. Here's the briefs.
Sure.
And but yeah, so there are, and so we have automotive and sort of consumer commercial variants of this product. Okay. So, and you're right that basically a big focus today is on fusing an airborne and a structure-borne sensor to give things like wind noise immunity, and stuff like that. So yeah, that's definitely it. Okay, so that's sensors. So we've done models, cutting-edge models. We've done sensors. This is our most recent sensor. We have, of course, a complete portfolio of digital and analog microphones with a range of SNRs and costs and overload points and all those things, protection, and so forth. So finally, I won't do a discrete introduction to our latest chip, but I'll do a kind of an integrated one that shows, the sorts of things we're aiming to deliver. And from our perspective with the platform, our belief is that for customers that want to use the whole platform, rock on, use the whole platform. If you want to use just components of it, rock on as well, right? I think what happens, which is my experience from previous industries as well, is that when you deliver a complete solution end to end with all the parts to production, every part becomes better. So basically, you'll end up with a superior sensor when you think about all of the end to end pieces, and we're just starting to do that. Historically, the sensors, basically the cell phone vendors have driven a lot of the functional partitioning and functionality expectations in terms of power and performance and things like that, because they buy most of them. The earbud products are, gaining, so probably more microphones sold through earbud products than phones. But between the two of them, they're kind of in the mobile universe. And so they're heavily specified and personalized in that area. Which is a big area. It's an important area. We're not leaving that behind. But there are a lot of other systems, like this. This is an example here that don't fit into that category. And I'll talk a little bit about this one just to see all the different pieces and parts that you can start to do when you look at an end-to-end solution. Okay, so here on the left basically is your sort of typical automotive central compute module. It could be Qualcomm or NVIDIA or something like that. And then it's got connectivity that goes out to, over a typical car, 4 camera surround view system, 2 on the mirrors, 1 on the front, 1 on the back. Okay. And so historically, this is just a sensor. Okay. So 3 megapixel sensor is typical for surround view, 8 megapixel for, autonomous driving and ADAS type capabilities. Okay, so then let's say you want to add capability beyond. So that historically those are only active when the vehicle is in operation because it's generating energy or whatever for internal combustion for gas burners or whatever. So now you say I want to do more with that. Okay, with that, you basically have rich connectivity, you have rich sensors, high bandwidth, that kind of stuff. What else can we do with that? So a security capability has been deployed on a number of cars, which basically is always watches and always listens. Okay,
Yeah.
so that will allow you to, protect your car, deter people from going for your car. So, for example, just like it was with stealing vehicles, they know these cars don't have the immobilizer fobs or whatever. Steal that one, not this one.
Right.
So go after the car without the security, not the one with. All right.
Yeah.
So that's essential.
Yeah. Back when I was in high school, there was a crew of hoodlums that knew which cars they could get into easy for the car
Correct.
stereo business. The
Correct. Correct.
aftermarket.
Exactly. 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 So,
Yeah.
so the name of the game here is to, what the user is looking for is to deter people from going after their
Right.
car. And then we also have technology deployments where it's things like commercial vehicles where the objective is payload protection. Okay,
Mm.
so I have a bunch of expensive tools in my van
Yeah.
or something in the bed of my truck. Again, same objective, which is to deter people from going after systems that going after trucks that have this kind of protection or cars or whatever. Okay,
Right.
so let's look at today what happens is with the security systems that exist today, use sight and sound, they are only feasible on full electric vehicles that have massive battery banks. Okay, and so they consume more than 100 watts, okay, basically just sitting there. And if you know the math on the battery bank, it's you're not going to flatten that big old battery in a couple of hours. But even with the electric vehicles, one of the challenges that everybody experiences, even with a full EV, is you drive into a parking garage in an airport with a quarter of your range remaining, and you go away for a few days and you come back and you're down to an eighth or less, and then all of a sudden you have a range anxiety moment. Okay, so even for EVs, the solution is functional, but it's a pain point. Okay, and for internal combustion and hybrid, it's impossible to deliver at this approach. So basically, what happens is the sensors are on, everything is power mitigated to a certain degree, but it's running processing in the central compute. Okay, so instead, what we can do with the Syntiant technology, so this is the NDP 250 in this camera module in this case, and it is our most recent Syntiant Core 3, that's our processor generation device. I know you did a Total Harmonic with the first generation with James, right? Syntiant Core 1. You've done.
Yeah, I think it was Dave Garrett.
No, actually, you did. First one you did
James
was with
Fife.
James Fife.
Right.
In Irvine.
Yes, that's
In
right. Thank you.
Irvine. Okay, so that was Syntiant Core 1. And then
Okay.
Dave Garrett was Syntiant Core 2.
Okay.
So you stuck with Steph Bailey for Syntiant Core 3,
All right.
where, we this is our Syntiant Core 3 one. We don't have to have just one, but we have a lot of other motion in the business as well. So we're not going to just talk bits and bytes about Syntiant Core 3, but realize that each generation is, significantly improved from the previous one. And again, the key is map lots of models and deploy lots of, customer outcomes as well as our own. It's just like conventional processors over generation, you would add features and capabilities to run things people want. So this is our third generation. It's been on the bench about a year.
Mm-hmm.
And the fourth generation is under development. So this is a very, very, very capable processor. This device, it's on the website with a brief, but basically it has 6 times the neural memory of the NDP 200, which was the visual version of the previous one. It has 5 times the neural throughput. It's got a more robust extensor core. And essentially works for much larger format vision inputs, and it has audio interfaces as well. So the scenario here, how we get this thing so that it runs in under 100 milliwatts, which is something that would then give you a month at least of endurance if you came in full just on a starter battery, with an internal combustion car. So you 1,000x better gives you really solves the endurance problem. Okay, so basically the way this works is the NEP250 will look at the sensor input in a low power, low format mode. Okay, so the sensor is a 3 megapixel sensor. If you're building a surround view picture, it's going to be 3 megapixels at 30 hertz or something like that. It gets stitched together in the central compute, so you can see nice surround view. But the deep learning part of it doesn't need to run at that resolution or nearly that fast. The deep learning part basically is responsible. The first part of it is, as I mentioned, on the vision side, a visual detector. So is there something I care about within this view? Okay, and tell me where they are. Give me. I find all of the Shiba Inus in this scene or whatever. Okay, so it's running, and that is running at under, with the sensor plus the NDP, under 20 milliwatts. We'll probably get to under 10. Okay, so it will run with high accuracy. It will see things. Okay, so then the architecture here, imagine you started with the security solution just like you would in an EV, Chinese or a Tesla or something like that. Multiple of these cars have this solution. Mm-hmm. And then your goal here is just to make sure that 100-watt beast is not running most of the time. Okay, right. So you have a fully capable solution that runs on your central compute. The name of the game to make it last a long time is to just make sure it doesn't run when there's nothing to see. So, okay, so you see the Doge here, and then you say, okay, so this is a problem, I don't know. So then what you will do is you will basically notify back up to the central compute, hey, I see something that wasn't there before. So there's no Doge, and then there's a Doge. Okay, so then central compute and everybody will turn on the sensor to full resolution and full rate and look carefully. Okay, so the detector models here, these little brain things, that says find all XYZs there. So that's what runs on the sensor side. And then on the central compute side, that identifier model, like that visual transformer, will say, I'm not really worried about that thing. Okay, you saw something, but I'm not worried about it. So I'm going to go back to sleep and you tell me if anything changes. Okay, so then the NDP250 will continue watching. And if, for example, the box gets bigger, that means it's getting closer, then you go back to central compute and say, hey, something is happening. Or if another one comes, wake it up. If it gets smaller, ignore it. Okay, so with that simple control strategy, you can go from 100 watts to 100 milliwatts. And then similarly, sound is also a critical part of the security scenario. If there's a massive bang or something crazy that you hear, you definitely want to notify the user. And then what's the outcome? It usually goes and notifies the person on this watch or something. Dial 911. Right. Should I push the 911 button? That kind of thing. And so sound has the ability to see around corners. So if there's stuff in front of you, sound is a critical piece of it as well. And finally, with the V to S sensor, it also has the ability to detect vibrations directly. So another thing is if somebody hits the car, or bumps into it, that's another security relevant event that then goes back to the brain, which looks closer and does threat analysis. Okay. And but wait, there's more. That's one capability you can do with this chassis. Another capability is to allow exterior speech interface. Okay. So the example there is today, when you want to open the tailgate of a lot of these cars, there's an ultrasonic sensor that beams down and you put your foot under it and then it opens up. Okay. So that clearly is not the perfect interface. It's functional. It's better than dropping all the stuff in your hands and stuff like that. And it actually combines proximity of your fob with your foot under there. So not anybody can put their foot under there, but be easier to say, open the trunk. Okay.
Right.
And so the V to S sensor has the ability to pick that sound up in an economical, way with minimal protection. So you can talk to the device, you can talk to the car through the same means. And then finally, you can combine in terms of the total interface of people to the vehicle. So one thing that everybody likes to talk about is California law for autonomous vehicles requires first responders to be able to communicate through to an operations center through the vehicle starting next year. Okay, so that basically is going to drive external sound interface requirements. So this kind of chassis can address that. And then finally, any visual interface you want to do, help, I'm in distress, or, open it up or crank up the tunes or anything like that. All can be done with this basic chassis in a very energy efficient way. Okay, so the key is it's ambient, which means it's always on versus when the car is in operation. So and then back to what's Syntiant. Syntiant is the sensors, at least the sound pickup sensor, not the vision sensor, the low power neural processor, the models that run on the module that are essentially the sentinel pieces of it, wake me up when you need it, and then some of the models that would run over on the central compute. Like if you wanted to have a voice assistant there that doesn't require running up to the cloud and back down, which you don't want, right? Because you don't know if you have connectivity. Those kinds of models are things that we also provide. But not the total solution, just building blocks. So you build whatever you want with that.
Sure.
So I've talked a lot.
Yeah.
That's I went through our three things. Now they work together. So
it was very fast and very dense. But I was curious about one thing. So things like the hardware microphone is pretty, relatively easy for normies to understand. But the terminology around the model and the number of parameters and things like that is a bit more of a vague general concept. How do they come about?
Yes.
Do you provide that? Do customers make their own? How do they do it?
Yes, that's an excellent question, Simon. And the question of the ages, in a way, I think the challenge is, so one answer is that building models is as specialized an expertise as, say, building chips or MEMS transducers, which means there's a combination of understanding and expertise that goes into creating them. Okay, and it's a totally different cycle. So one of the challenges,
on that point, if you don't mind, does that mean that coming up, there's a spawning new industry of engineers who are model creators, like there might be firmware guys or chip designers, there's going to be model?
There are. Okay, there are. And most of those model creators right now are off building the enormous models, ChatGPT, all those. Okay, so that's where the richest activity is today. Okay. And we always had this problem, like I'm a software person, but I was a hardware person originally and then a software person. I've been a software person in chips companies a long time. Chips people understanding software people is hard. And then software to modelers and ML people is another step into space alienness. But yes, absolutely. There's lots of zillions of resumes, lots of interests, and basically most of the model attention today is using models to drive application outcomes that it's magical for. What we focus on is models for interface that have different performance expectations. One of the things about interface stuff and all these terminal devices is generally it has to work before you ship it out, and you have to be really, really, really confident that it's working. Okay, so you're not going to ship something that you're not really sure about. Whereas in the application space, again, you can't go crazy with it, but you can introduce a feature to a small subset of user population to figure out, do they like it? Do they not like it? So that's one of the many reasons why application development in the cloud is just so much better than out on remote devices. But in the end of the day, I don't think either is easier or harder necessarily. They're different. So yes, we got a bunch of modelers. We have maybe 15, 16 out of, maybe the 70 that came in with Syntiant, and we'll grow more. So yes. And then it comes down to a degree of expertise, a degree of common practice, general understanding of how it works, and it's an empirical programming model. That's the other thing that's hard for people to get their heads around. So my first prezo from Syntiant was TinyML, where I basically, I had a cute little picture of like, we have geniuses building signal processing programs. Okay, that's the way in sound, that's the way we've done it. And then we have hammer mechanics like me that were never signal processors, who basically are having back propagation, building the programs. We're giving it the data, it's making the program, and then we're figuring out if it did right and then adjusting the input. Okay, so it's a totally different programming model. And the benefit is that it can do magic that generally humans can't do. Okay, the other thing I think is the unspoken piece of it is that it actually allows people who are not subject matter experts to do equivalently to a subject matter expert. So that's, I think, a little scary to some of the subject matter experts. But yes, that is a key. Yes.
Interesting.
And so there is part of it that we start to hear more and more about how the parts of developing an AI or machine learning or this type of thing are getting categorized out into different components that you look at.
Yes.
But for now, that's not really something that's accessible to your customers for the chips. You have to deliver them the system.
No, it is. Okay, so there's a few different ways. How do you develop? So generally, you develop a model using what's a common flow. Okay, here's data, here's the back propagation, here's the evaluation, here's the analysis, and then you go around and then you take it in a lab and you take it in the real world. So that flow is the same, okay, no matter what types of models. Now, in terms of and then in the middle of that are training frameworks. So things like PyTorch is the new one. When we started, TensorFlow and Keras were the ones that everybody was using, particularly towards embedded devices. And then there's a ton of code and other stuff around it to create models. So if you look at very, high-flying, highly valued companies for application deep learning, like Scale AI is an example, which was just in the news recently, a lot of them are tooling, pieces and parts of tooling for application outcomes. Okay, so there are not really any. That part, the application part, is broken down into a lot of different pieces, and people offering various pieces parts like enterprise software. On the interface side, the tooling to build high performing models from a given data set are much thinner on the ground, I would say. So, for example, there are a number of platforms. NVIDIA has one, Intel, been trying to sell it away. There's a few for vision, okay? There's really none except, so Syntiant, we do offer our tooling platform, sort of early engagement now. We've sold it to some customers and we'll expand it more. So customers can use it as a programming tool, or they can use their own. So if it's, let's say it's somebody, Google or something like that, they have lots of tooling. Okay, so they just produce their models. And then if it's somebody who's just started from scratch, I think that the goal that we try and aim for is, let's say you have somebody who knows how to do modeling. Okay, so they understand that part. They're not trying to learn that part. So one of the problem statements when we started, which I never thought was satisfiable, and I think I've been proven correct, is help an inexpert person produce a quality model. Okay, I don't think that's possible, right? You have to become an expert in the modeling activity. Doesn't mean you can't learn, but it can't be like, I don't know how this thing works. I don't know how modeling works. I just want you building a model. So if the problem statement should be for these frameworks, these pipelines is, I have an expert, I have data, and I want to get to a production model. And let's presume the data that I have is enough to get to a production model, hypothetically. That's part of the process, by the way. But then the tooling should be such that I can do that quickly. Okay. And so Syntiant's modeling platform, which I didn't mention here, is one option. And then, there are some other ones out there. But yeah, it's pretty early days in terms of the tooling options. And ours focuses on, it's maybe a little bit less nice. It's really what we use, that we've always had an eye towards merchanting so that our customers, we don't want to build all the models, right? We offer the models that we offer, and our expectation is like, use what we have if it's suitable for you. We also are in the business of personalizing, but generally speaking, we just want to get deep learning driven interface systems out there. And just like conventional computers, I started out at DEC back in the day. We build chips, systems, operating systems, databases, middleware, applications, the whole thing. But even with that set, the computer didn't come to life until somebody added some code, right? Almost nobody just said, hey, all the applications you provide, everything is perfect. I don't need to do anything else. We need to get to the same state here, with deep learning, where unique and new stuff, the device people will develop for themselves. Common stuff like these detectors, everybody has them. Okay, they're, it's like you built it yourself or whatever. Not the people that don't have it, of course, but there are many detectors out there, and so that's not something necessarily that will differentiate your product. You need that, or your product just won't be viable at all. So yeah, so it's definitely a developing area. It's a good question.
Heavy.
Yeah, right. I know, right?
I know. It's
completely disruptive change. In 10 years, or I don't know the number, it's going to look like that next thing up with deep learning driven everything. It's going to be totally different. Yeah, that's right.
All right. Good stuff. Simon, any more questions?
No. Yes, but it's just
it'll come back to us.
We'll do it in the next one. Exactly.
Anybody else anyone else with questions, just shoot them down below. We'll see they'll get passed along to somebody, but we'll put all the contact info so people can look up more on Syntiant below as well. And thanks, Steph. Thanks for joining us. Let me know next time you're passing through Hong Kong. We'll catch up again. And thanks, Simon. So thanks, everybody. Like, subscribe, all that good stuff, and we'll see you on the next one.
Very good. Thank you, guys.